Here we are going to learn how to quantify how curvy a curve is using the notion of curvature. Curvature is going to measure how quickly a curve changes direction. If you think about that, that would mean that straight lines have no curvature. It also means that the tighter a curve is, the larger its curvature. So in other words, the curvature of a globe is going to be significantly higher than the curvature of the Earth. Since curvature is intended to measure how quickly a curve changes direction, we're going to define it as the magnitude of the change in the unit vector with respect to the arc length of the curve. In other words, kappa, the letter we use for the curvature, is going to be equal to the magnitude of dt ds, where t is the unit tangent vector and the parameter s represents the arc length of the curve. We rely on the parameter s here because the curvature should not depend at all on the velocity with which we traverse the path. Think again of the example mentioned previously. Whether we traverse the circumference of the Earth in a boat or a plane, the curvature of the Earth doesn't change. Only the speed with which we get around the Earth changes. This definition guarantees that curvature is independent of velocity and that curvature is measuring how fast the tangent vector is changing per unit of arc length. It can be tricky sometimes to reparameterize a function that isn't parameterized by its arc length. So instead we have this occasionally more practical formula, kappa equals the magnitude of the tangent vector with respect to t divided by the velocity or the derivative of r with respect to t. Let's see how these two formulas are related to one another. If we start off with the idea that kappa is the magnitude of dt ds, we know that from the chain rule, this is dt, the same as dt times dt ds. Let's see if we can get a grip on what this looks like. We know that s of t is the integral from 0 to t of the absolute value of r prime of u du. The fundamental theorem of calculus then tells us that ds dt, if we take the derivative of that function with respect to t, we get that is r prime of t, or the magnitude of r prime of t. Well then, that tells us, by taking the reciprocal, that dt ds is 1 over the magnitude of r prime of t. Plugging that in up here, we get that this is the magnitude of dt dt times 1 over the magnitude of r prime of t, but dt dt is just t prime of t, so we have the magnitude of t prime of t over r prime of t, the magnitude of that quantity. We have one last formula for kappa. Here kappa is the magnitude of the cross product of the acceleration and velocity divided by the magnitude of the velocity cubed. The derivation of this particular formula is more than I want to do in this video, but do keep this formula in mind because it occasionally works out to be much simpler than either of the previous ones we've seen. Let's look at an example to maybe establish some more intuition about this idea of curvature. So here we have the curve r of t equals a cosine t, a sine of t, 0. We know that this is a circle with radius r. Radius a. Okay, and we said earlier that the smaller a circle is, or a sphere, the more curvature it should have. So hopefully when we come up with the formula for this curvature, we'll see that reflected in that formula. All right, so we're going to use the formula that kappa, it's just kind of a funny looking little k, is going to be the magnitude of t prime of t divided by the magnitude of r prime of t. Well, first let's find the vector t, which we know is r prime of t over the magnitude of r prime of t. So that is going to be the vector negative a sine t, a cosine t, 0, divided by the magnitude of that, which we can see pretty easily is going to be a, because we get a squared sine squared t plus a squared cosine squared t, and then we take the square root. So in other words, t is the vector negative sine t cosine t when we divide as 0, when we divide everything by that, by a. So t prime then is the vector negative cosine t, negative sine t, 0, and the magnitude of t prime is going to be the square root of cosine squared plus sine squared, so that is 1. We already saw that r prime of t was a, right here, r prime of t is a, so when we plug into the formula for kappa, we get 1 divided by a. So let's think about our circle. This tells us that the larger the radius of the circle, we have smaller curvature. All right, let's try another one. We have the curve r of t equals 3t minus 1, 4t plus 3t, and we want to compute its curvature. Now, if you can look at that and tell the answer, you're doing great. If not, that's okay. We're going to work it out and see what happens. So we need the vector t first, which is going to be r prime of t over its magnitude, which is going to be the vector 3, 4, 1, divided by the magnitude of that, which is the square root of 26. So we get the vector 3 over root 26, 4 over root 26, 1 over root 26. Okay, now we have to remember that kappa is the derivative of that, the magnitude of the derivative of that, divided by the magnitude of the derivative of the velocity. But t is a constant vector. T is a constant vector, which means it's not changing at all with respect to t or any other parameter. So we get 0 over the square root of 26, which is 0. Now, maybe some of you realized this at the beginning, but this curve right here, this is a line. So it makes sense that its curvature is 0 because it's a straight line. All right, for this one, I'm going to use our alternate formula. So remember we had that kappa was equal to the magnitude of v cross a over the magnitude of v cubed. I think earlier maybe I had it as a cross v over the magnitude of v cubed. Now normally v cross a is not the same as a cross b, but since we're talking about magnitudes here, they are in fact the same. They're pointing in opposite directions, those two vectors, but they have the same magnitude. So either way works. So let's look at v. V is going to be r prime of t, which in this case is going to be 1, 2t, 0. And then a is, of course, v prime of t, which is going to be 0, 2, 0. So if we look at the magnitude of a cross v or v cross a, either one works, we're going to get, for no magnitude first we'll just do the vector. So I'm going to do v cross a. And again, if I do it the opposite way, it doesn't matter in this case because we're talking about magnitudes, not the vectors themselves. So v cross a, I have 1, 2t, 0, and 0, 2, 0. And that's going to give me the vector. Let's see, I get 0. And then 0, and then again, When I do k, I get 2 minus 0, so that's 2. And to help build your tuition again, notice that r of t lives in the xy plane. And so its vector, its velocity vector, and its acceleration vector live in that same plane, which means their cross product has to be orthogonal, which means that's why it only goes in the direction of k. So the magnitude then of v cross a is going to be 2. The magnitude of v is the square root of 1 plus 4t squared. So our kappa in general is going to be 2 divided by 1 plus 4t squared to the 3 halves. But notice we were asked in particular to find the curvature at a value of t equals 0. So kappa when t equals 0 is going to be 2 over 1 plus 4 times 0, which is 2 over 1. And so we get a curvature of 2. All right, last example. I think this might take us on kind of a wild ride. Hopefully we can get through it, avoiding too many sign mistakes. I'm going to do this one straight from the definition of kappa as the magnitude of t prime of t divided by the magnitude of r prime of t. So we'll start off with r of t, or r prime of t rather. We have to use the product rule for this. So we're going to get e to the t times cosine t plus or minus sine of t, or minus e to the t sine of t as the derivative of the x component. And then we're going to get e to the t sine of t plus e to the t cosine of t as the derivative of the y component, and e to the t as the derivative of the z component. I'm going to rewrite that a little bit. I'm not entirely sure it'll make life easier, but I'm going to do it anyway. So I'm going to factor out e to the t from the first and second terms. Okay, so now we need to find the magnitude of that. So the magnitude of r prime of t, because that's going to be useful in calculating t as well as calculating kappa. So the magnitude of that is the square root. This I may run out of room here. I'm going to do my best to squeeze it in here, but we're going to do the square root of e to the 2t times, when I square that out, I get cosine squared of t minus 2 cosine t sine t plus sine squared of t. And then the middle term, when I square it, I get e to the 2t, and then I get sine squared of t plus 2 cosine t sine t plus cosine squared of t, and then I get plus e to the 2t. I made it on one line. All right, still I'm going to factor out an e to the 2t. And then when I combine terms here, I have a cosine squared t, the negative 2 cosine t sine t, and the positive 2 cosine t sine t are going to cancel each other out. So now I have cosine squared plus sine squared plus sine squared plus cosine squared plus 1, which altogether gives me the square root of e to the 2t is e to the t. I have e to the t root 3 when I simplify that. All right, now we're going to find t. So our vector t is r prime of t divided by the magnitude of r prime of t. We already found r prime of t, so now I'm going to divide it. So I'm taking this vector right here, r prime, and I'm dividing it by this magnitude. Notice that all of the e to the t's are going to cancel out, and I'm going to end up with the vector cosine of t minus sine of t, sine of t plus cosine of t, 1, all divided by the square root of 3. That is my vector t. Now we get to do t prime. T prime of t is going to be negative sine t minus cosine t, cosine t plus, minus sine t, 0 all over the square root of 3, because the derivative of a constant times the function is the constant times the derivative of the function. And now we're going to take the magnitude of that guy. So the magnitude of t prime of t is the square root, got another giant square root, of, let's see, squaring this, we get sine squared of t, and then we're going to get plus 2 sine t cosine t, plus cosine squared of t. That's from the x term. The y term is going to give us cosine squared of t minus 2 sine t cosine t plus sine squared of t. And of course, we're dividing each of those by the square root of 3 squared. So this is all still divided by the square root of 3. We can tidy that up. T prime of t, the magnitude of that is sine, these guys cancel. I have sine squared, cosine squared, cosine squared, sine squared, so I get the square root of 2 over the square root of 3. Going back to kappa, kappa is that magnitude, square root of 2 over the square root of 3, over the magnitude of r prime of t. The magnitude of r prime of t was e to the t root 3. So we get root 2 over root 3 times 1 over e to the t root 3, which simplifies to square root of 2 over 3 e to the t as a formula for our curvature. All right, so we've seen that curvature can be a little computationally messy, but if you can keep some ideas in your mind about it, it might help you develop some intuition. So curvature is measuring the bending of a curve. If it has no curvature, that means we're moving straight. The higher the curvature means we're turning on a tighter turn. And it's really important to remember that curvature is a geometric property of curves. So it's independent of how we're moving along the curve, which means that the parameterization we choose for a particular curve doesn't impact our computations for its curvature.